Hi there. Welcome to lecture 18 of Machine Learning from Data. We're going to be discussing radial basis functions. Okay? And we're going to derive radial basis functions as a soft way to extend the k-nearest neighbor algorithm. So let's see what we were doing last time. So last time we addressed a couple of the challenges posed by implementing the k-nearest neighbor algorithm. The first is memory. You have to cart around all the data to classify a test point. So we introduced data condensation, and in particular, how to condense the data, or an algorithm, condensed nearest neighbor, for condensing the data to in some sense, a sufficient set, a subset of the data that is consistent with the original data, at least with respect to the classifications on the training points. Okay, and we saw with the digits data that you can get some remarkable reductions in the amount of data needed to be kept in order to stay consistent for the training set. Okay. And that addresses memory and also, the efficiency aspect, because if the data set is smaller, finding the nearest neighbor and classifying a test point is also going to be quicker. Okay, but given a fixed data set, we independently addressed the issue of how do you quickly find the nearest neighbor. Now, in the worst case, if you absolutely must get the nearest neighbor, you might have to, run an O of ND algorithm, N being the number of data points and D the dimension. But if the data is well structured into tight, well-separated, clusters, then we discussed a branch and bound algorithm which can significantly save on runtime. Okay, and the idea there was, when you're searching for a nearest neighbor, do the natural thing. Search first in the closest cluster, and then, when you find the closest neighbor in that cluster, it's possible that you can rule out all the other clusters. Okay, and so then you don't have to search them, and you get a huge savings gain. Okay, and we addressed a little bit, the task of how do you put the data into, even if the data can be clustered into tight, well-separated clusters, how do you find those well-separated clusters? And we discussed, Lloyds algorithm, which basically, attempts to find cluster centers that are as far apart as possible, and then, assigns points to each of those cluster centers, and then, the idea being that since the cluster centers are very far apart, you are likely to get clusters which are far apart, and you only assign to a center the point that are close to it, so hopefully the clusters are also tight. Okay, and so coupled with a good clustering of the data, the branch and bound algorithm can significantly save on runtime. Okay, now today we're going to discuss softening the k-nearest neighbor algorithm. And what do I mean by softening? Well, the k-nearest neighbor algorithm uses the k-nearest neighbors, and that's it. Okay, and there are all these n minus k other data points that you seem to be ignoring with respect to the classification of your test point x. And so a natural question is, what about using all the data to classify your point x, your test point x? Okay, but if you're going to do that, then you should probably give more weight to the more similar data points and less weight to the very different data points, i.e. the data points that are close by should get more weight, and the data points that are far away should get less weight. Okay, and when we discuss this sort of extension of the nearest neighbor algorithm to allow it to use all the data, we will ultimately end up with what's called the radial basis function and the radial basis function network. Okay, so let's go to the board. Okay, so what's the idea? The idea is that we're going to use all the data in order to predict at the test point x instead of some of the data, as we did with the k-nearest neighbor. Now, we're going to describe the radial basis function. Okay, in particular, we're going to start with what's called the nonparametric radial basis function. Okay, and I'm going to show everything. I'm going to and we'll illustrate in one dimension, but everything carries over to d dimensions, no problem. And we're going to focus mostly on regression because it's easiest to sort of show the results for regression. And I'll mention, how everything carries over to classification and also to logistic regression. Okay, so let's begin with the k-nearest neighbor classifier. Okay, so k-nearest neighbor. Okay, and what's the final hypothesis? The final hypothesis, g of x is equal to the sum over your k-nearest neighbor, so from I equals 1 to k of it's actually the average value of the y, is the average y value. Okay, so it's 1 over k, y square brackets I. So just to remind you, the square bracket I means, take the data points and sort them, order them according to, the closest has, square bracket 1, then next closest, and so on. And these are the y values for those k closest data points, and then you take the average. Okay. Now, it's convenient to view this this average as, a weighted sum. Okay, so this is, I'm going to take the 1 over k inside the sum. Okay, and now you can view this as a weighted sum where the weights of these k data points are 1 over k, so uniform weights, and then all other data points have weight 0. Okay, and this allows us to extend immediately to the nonparametric RBF. So let me say nonparametric. Okay, and nonparametric versus parametric we discussed last time. So the nonparametric RBF. So RBF means radial basis function, and now we're going to use all the data to classify at X. Okay, but instead of using uniform weights, we'll allow the weights to be picked. You can pick the weights, and they can depend on the data point X. So here, here the weights also depend on the data point X by identifying the k closest neighbors. Those guys get weight 1 over k, and then all the other data points get weight 0. Okay, so the nonparametric RBF final hypothesis. G of X. Now we're doing regression, so we're going to take the weighted average, okay, of the y values of all the data. So the sum from n equals 1 to big N of a weighted average. So we'll define weights. Okay, let's call it alpha n of X. So here the weights were just 1 over k. Now why alpha n of X? Well, because the weight depends on the data point and also on the test point. Okay, so how much a data point gets weighted depends on the data point and the test point. So the same data point might have a different weight for a different test point. Okay. Now, since these weights may not add up to 1, we should normalize them so that it becomes a sort of standard weighted average. So we'll normalize the weights, divide by the sum over m equals 1 to big N of alpha m of X. So this is normalized weights. So weights normalized to 1. Okay, so these weights are playing the same role as the 1 over k. And now you just take the weighted average of all the y values y sub n. Okay, so just simply porting over the final hypothesis from k nearest neighbor to the situation where you use all the data and you appropriately weight. Okay, and that's it. That's the nonparametric radial basis function. Okay, and the only thing we need to discuss now is, well, how do we pick the weights? Okay, so imagine the following picture. Okay, so you have your test point X. Okay, and your data points are spread across the space, and so you have a generic data point, let's say xn. Okay, and I want to pick the weight that xn has on X. So what I can do is I can define a function. Let's call it a bump. So I'll place a bump on X, a decreasing bump. So it has some height at X. So data point that is at X will have the highest weight, and then it's a decreasing bump as you move away from X. And this height here of the bump at Xn is exactly what we're going to call alpha n of X. Okay, alpha n of X. You've placed a bump, and on the test point, and as you move further and further away from your test point, the bump is decreasing, and so you get a smaller and smaller weight. Okay, and we can call this function, phi, okay, this bump function. Well, technically we call it a kernel, so this is called a kernel. Okay, and let's see now, what should this kernel, how should this kernel behave? So this kernel, so alpha n of x is going to equal phi of something. Okay, and let's see if we can figure out what the weight should depend on. The weight, so this is, let me be very specific, this is the weight of data point xn at test point x. Okay, so what should this weight depend on? Well, this should be a decreasing function of how far the data point is from x. Okay, so it should be a decreasing function of the distance between x and xn. Okay, but now we can sort of be a little street smart and realize that the data may have some intrinsic scale. It could be meters, centimeters. It could be thousands of dollars, hundreds of thousands of dollars. So when you collect your features or you collect your data, it's measured in some scale, in some unit. Okay, and the units in which we should measure the distance should be that scale, the intrinsic scale of the data. We can think of that as being defined by a scale parameter r. Okay, so we should measure distance relative to a scale parameter r. So this is the scale parameter. Okay. You could think of it, you could imagine that the scale parameter r could be, for example, the radius that encloses all the data, or 1/2 of that radius. It's essentially, the intrinsic scale of the data. You should measure distances relative to this intrinsic scale. Okay, and there you have it. That's it. You can specify any decreasing function you want for phi. Okay, so let me give you some examples. Okay, you could specify phi as 1 over 1 plus, so phi of s, okay, so phi of s equals 1 over 1 plus s squared. So as you move, as the argument gets bigger and bigger, it's dropping. Okay, you could specify phi of s as, okay, so you could specify phi of s as equal to, 1 if s in absolute value is less equal to r, and 0 if s in absolute value is bigger than r. Okay, so let me show you what this looks like. So this guy is sometimes called the window kernel. Okay, so at 0, so you have r, and it looks like this. Okay, so I'll draw it in red, nice red color. Okay, so here, boom. Okay, so that's the window kernel. Okay, so what is it doing? Basically what this does is it says, you're at a test point x, so at x, the argument is 0, so you're at a test point x. You collect all data points that are within my window of x and weight them equally, and then compute the weighted average. Okay, so that's this window kernel. That's a fairly popular kernel. This kernel here is not that popular, not very well behaved, but by far the most popular kernel function, the most popular decreasing function that decreases and as you move away from the test point, the most popular phi of s is equal to e to the minus s squared over 2. This is called the Gaussian kernel. Okay. So this is called the Gaussian kernel. Okay, and let me show you what that looks like. So here's your test point x at s equals 0, and as you move away from the test point, so here's the maximum, and it drops, and then it drops very fast. Okay, so it has the effect of, it doesn't ignore any points. Okay, but once this argument here goes beyond 1, when it goes beyond, for example, 5, you're basically weighting those points as 0. So it's a soft version of the window kernel, in the sense that, if you're close enough, you've got a reasonably high weight, but once you go far away, your weight drops very rapidly to 0. Okay. So, this is by far the most popular. It's not that different from the window kernel, but the window kernel is very hard to work with. This is nice, smooth, continuous, and has a very thin tail, what we say thin tail. But you could, in theory, pick your kernel function. Okay, and so, your final hypothesis, g of x. So now, your final, let's box it. G of x, okay, is equal to the sum from n equals 1 to big N, okay, alpha n of x over the sum over m equals 1 to big N alpha m of x, y n, where alpha n of x is equal to phi of x minus xn divided by r. Okay, and I'll box it. Okay, so this is the radial basis function, the non-parametric radial basis function for regression. And now let me mention quickly, what we do for classification. Well, for classification, these y's are plus or minus 1, so you just take the sign. Classification, take sign. So g of x is equal to the sign of the sum from n equals 1 to big N, alpha n of x, divided by the sum over m, alpha m of x, y n. Okay, very simple. That now gives you a classifier. Okay, where instead of taking the weighted average of the y values, you take the weighted average of the plus or minus 1s, and then take the sign. Depending on whether this is positive or negative, you classify. Logistic regression. It's just as easy. So instead of taking the weighted value of the y values, okay, in logistic regression, the y values are plus or minus 1. You take the weighted proportion of y values that are plus 1. You take the weighted proportion of y values that are plus 1. So g of x is equal to the sum from n equals 1 to big N alpha n of x over the sum from m equals 1 to big N of alpha m of x. Okay. Now instead of the y value, you just count. You want the weighted proportion. So you count 1 when it's plus 1 and 0 when it's not plus 1. So you're just counting the proportion of 1 of plus 1. So we need the indicator of whether or not yn is equal to plus 1. And there you have logistic regression. So this is the weighted proportion of plus 1s. This is just the sign of the weighted average. Okay. And that corresponds to, in the k-nearest neighbor, you would have taken the sign of this guy to get classification. You just take the sign here. And, this is the nonparametric RBF, nonparametric radial basis function for regression. Now let's look at this. Okay. The only thing you need to do is tell me what R is. Okay. Basically, it's determined by the scale of your data. Okay. And if your data has been normalized and so on and so forth, which we will discuss later, then you can even choose R equals to 1, for example, in which case there are no parameters here. You're ready to classify. You are ready to classify. Okay. And that's it. Boom, down. Okay. So now let's see, some examples of this nonparametric radial basis function in action. Now, and it'll become clear why we're calling this the nonparametric, because it's just like the nonparametric, nearest neighbor model. There are no parameters to learn except for this R, which is not really a parameter to learn. It's just an intrinsic scale of the data. You're ready to classify the, test point the moment you get the data. There's no training and so on and so forth. And we wonder whether the other properties of the k-nearest neighbor will also carry over to the RBF. Okay, so let's first see some examples and then discuss further. Okay, so in the slide we're illustrating the nonparametric RBF in comparison to the k-nearest neighbor. Okay, now this is some regression data, the blue circles in one dimension. The little light gray curve is the target function, so we've generated some data with a little bit of noise. Okay, and let's focus on the top row, which is the k-nearest neighbor when k equals 1 on the left, then k equals 3, and then k equals 7. Okay, and what do we observe? When k equals 1, it's sort of like, perfectly fitting the data. Okay, and then when k equals 3, you've got a reasonably nice, smooth fit. And when k equals 11, it's just, taking basically the average of all your data points. Okay, and, on the left with the k-nearest neighbor, that's the overfitting regime. K is too small. On the right, k is 11, that's underfitting, and, there's k just right. And we talked about how do we pick, the optimal k. Okay, and k equals 3, reasonable. Okay, we discussed this a couple of lectures ago. Or you can take k equals square root of n. Okay, that's what the theory suggests. Or you can pick k using cross validation. Okay, now bottom row. It's exactly the same setup, same data. Okay, except now it's the non-parametric radial basis function final hypothesis. Okay, and what do we get to pick? Just like we get to pick k in the k-nearest neighbor algorithm, we get to pick the scale parameter r in the non-parametric radial basis function. And we're in all these illustrations, there's going to be the Gaussian kernel. Okay, and what you see when r equals 0.01, so when the scale of my data, I'm setting it as 0.01, then, basically for this Gaussian kernel, only points that are very close to me will contribute to my prediction. Okay, and it's very similar to the one nearest neighbor. Basically, you're just capturing the value of the y value for your nearest neighbor. Okay, and that's the overfitting regime, r too small. Okay, and then we can set r very large, and it's analogous. So if the scale parameter is very large, then this number is close to 0 all the time, and so it's approximately a constant, and it's like the k-nearest neighbor for large k. So that's underfitting. And then there's the the best choice for r. Now, how could we choose that best choice for r? Well, one approach, just like k-nearest neighbor, is to use cross validation. Okay. Alternatively, we can go back to the analysis that gave us square root of n for the k-nearest neighbor and ask what value of r will give us effectively approximately square root of n of my neighbors, okay, the close by neighbors, giving me a significant contribution. So, if we want square root of n neighbors neighbors to contribute. Okay, and so you can think about it this way: there's the test point x, okay, and in this radius, the scale of r are the neighbors who are contributing. Okay, so what's the volume of this region? The volume of this region is proportional to volume, is proportional to r raised to the power d. Okay, and so the number of data points that fall in this region, so number of data points is going to be proportional to n times r to the d. Okay, because the probability of being in this region is some p of x, some probability, and then times the volume. So that's the probability to land in here times the number of data points is the number of data points that land in here, and we want that number to be approximately equal to the square root of n. So this means that r to the d should be approximately equal to 1 over the square root of n. So this suggests that you should pick r approximately equal to 1 over the 2dth root of n. Okay, so there you have it. A suggestion for the for the scale parameter that corresponds to choosing the k-nearest neighbor parameter as square root of n, and that works pretty well in practice. So this is just to show you that there really aren't that many parameters to pick. There are no real parameters to pick. You should pick this as the scale of your data. Okay, and if you want to pick, you should pick this parameter so that as your number of data points gets larger and larger, it's the closer data points, and there are many of them that are contributing. If this guy is getting too large, far away data points contribute too much. If this guy is getting too small, there aren't enough data points contributing. If this guy is just right, you have just the right number of data points contributing. Nevertheless, all data points contribute with some weight because this function is always positive. Okay, now. Let's summarize the nonparametric RBF. Okay, so first, it's just as simple as the k-nearest neighbor. Okay, so we have to implement some functions, some slightly more complicated functions, the Gaussian kernel. Okay, but basically, once you get your data, once you have your data, there's no training other than maybe heuristically setting r as we have shown below. But there's no training. You're ready to go and classify. Okay, if you choose r, as prescribed by 1 over the 2dth root of n, then you basically get the same convergence to optimal that you get for the nearest neighbor, and that's by okay. We're going to claim that by analogy, but you can sit down and make the proof. It's the same idea. If r is decreasing but not decreasing too fast, okay, with n, then you'll have enough data points contributing, and they will all be close. Okay, and so then you will recover the out of sample error. Okay. It's easy to do classification. It's easy to do logistic regression. Okay. It's easy to do multi-class. Okay. So if you're doing classification with multi-class, instead of the sign, okay, you just take the weighted majority. So each class will have a weighted contribution, and then you take whichever class has the largest weighted contribution. Okay. One of the other benefits of the k-nearest neighbor algorithm is that you can justify your classification, and you can justify your classification to the client here as well. So the client comes along and says, why did you approve? Well, what you do for your test point, you go and find which data points had the large weight, and here, these are the data points that contributed to the classification. So just as easy to justify. So you can justify, you can do logistic regression, classification, regression, you can do multi-class. I mean, it has all the benefits of the k-nearest neighbor algorithm, but it also has all the challenges. So what's the challenge? Computational demands. Okay, and it's for the same reason. You have to cart around all your data. The baggage is still there. Okay, you have to cart around all your data, and so there's the memory challenge, and then there's the computational challenge, the efficiency challenge. So let's see what we can do about that. Now, the obvious thing we can do is we can just run a simple algorithm to get rid of data. We can try to condense, but with the nonparametric RBF, we will find another way to address this challenge, and that will lead us to the parametric radial basis function network. Okay, and that's usually the way in which we use the radial basis function as the radial basis function network. So let's do that next. Turn off the slides, and I'll be back. Okay, so let's erase stuff that we don't need. Okay, so keep these two basic formulas, okay, and